All right. Continuing 2013 question 3. This one should look similar to something that we've done before, and we have done this with rotations. However, I do have to apologize because when I was doing this in class, I realized the difficulty of the problem, so I showed you a simplified way of doing it, which actually wasn't the most accurate. I'm going to show you exactly how to do this problem now. Alright, so starting off, this is easy. It wants to know what's the magnitude of force Fa, necessary to keep the disk at rest. Well, it's at rest, so should be easy enough. Just F net equals 0, so that means that Fa plus Ft equals mg. In this case, these two are going to be one and the same. So that's 2Fa equals mg. Which is going to be 20 divided by 2. So Fa equals 10. You basically get 1 point for stating that F net equals 0 and 1 point for the answer. Remember, it is important to write down that stuff. Alright. And now this is where we get to the very tricky part. This is where the bulk of the points are for this part. It wants to know what is the linear acceleration of the disk. Well, now the disk is accelerating upwards and it's rotating. And the thing to realize is that, yes, even though we still have the force Fa here and we still have tension, they cannot be the same. Ft cannot be equal to Fa. Otherwise, it would not rotate. The only way you can rotate is if you have a net torque. So if these two are both equal, then that means that it's not rotating. And in particular, we also don't know if Ft remains the same. So we can't say that it's equal to what it was before of 10 newtons. So we don't know that. So what we have to do is we have to go a roundabout way. Now if we use F net equals ma, we do the whole Fa plus Ft minus mg equals ma. Move things around. Like that. What you realize is, oh no, I have two unknowns. I know what A is, but I don't know what Ft is, and I don't know what A is. So, what we want to do is we have to bring in a second equation. So if you remember, the more unknowns you have, the more equations you need. If you have two unknowns, then you need two unique equations. This is one equation, F net equals ma. So this is my first equation. My second is dealing with the rotation. So tau net equals I alpha. We have FAR. Now this time, Ft is in the opposite direction. Because remember, when we do torque, we're not talking about whether it's up or down. It's whether it's rotating it clockwise or counterclockwise. This is Fa, and it's causing it to rotate counterclockwise. Ft is making it go clockwise. So these two are in opposite directions when it comes to torque. And then we're going to have mr squared, half mr squared for the I. And because we want to know about what the linear acceleration is, I'm going to replace alpha with A over R. Actually, this R is big R, this R is big R, and this R is big R. Alright, so I'll write from here, that R crosses out with that R. We have a R in each term, R, R, R. If If you don't believe me, you could double check. And we end up getting FA minus FT equals half MA. Alright, move things around. FT equals FA minus half MA. Alright, so again, I have two unknowns, but now I have two separate equations that I can use to figure out what the two unknowns are. So I'm going to take this and plug it back into my first equation. So I have FA plus FA minus half MA equals, I'm actually going to separate this, MG plus MA 2FA, let's see, minus MG equals 3/2 MA. So A is going to be equal to 4/3 FA over M minus 2/3 of G. So let's see, that's going to be, what's M? M's 2, so it's going to be 4/3 of 6 minus 2/3 of 10, so that's 20, and 24. I'm just doing this because I don't really have a calculator at hand. So you get 4/3, so you should get that the acceleration is 1.33 meters per second squared. That's a linear acceleration. Again, this one, the thing about this one is that you had to realize that you do two equations and two unknowns. So first, you got one equation for realizing you had to do this, and one equation for using torque, 1 point for this, for doing linear to angular acceleration. You got 1 point for this combining, and you got 1 point for the correct answer with the units. Alright, so that's where all your points come from. 5 points for this, and a lot of it required you to realize that you had to do two equations and two unknowns. Alright, before I continue, I should make mention of this statement. So just like what we did before when we had objects going up and down ramps, I said that though this is true, this A, even though this is true, equals A over R, this A is not necessarily the same as the linear acceleration. That's just a linear component of the angular acceleration. You know, the acceleration of a point on the edge of the disk. But when it does not slip, then that means that this is the same thing as this. So what I mean by that is that, let me give it as L. So even though alpha equals A over R is always true, when it does not slip, that means that this R is AR, A sub R. The same R over, AL is the same L that's in here. The reason why that's important is for this problem, because they want to know what the angular speed of the disk is at 3 seconds. So we know what the acceleration is, so we can use this equation. Alright, we know this is 0, so this is just going to be omega equals alpha t, but I don't have the angular acceleration. I know what the linear acceleration is, so I can replace this with A over R t. Plug and chug, and we should get 1.33, 3 seconds, and r was 0.1. So this should be about 4-ish, I think. Oh, sorry, 40. Yeah, sorry, that was my mistake. 40. So you end up getting 1 point for basically getting this, using that equation and getting it to here, and then 1 point for this. Remember, you do have to know what that term means, does not slip. What that means is that the linear acceleration is equal to the angular acceleration when using this equation. That the linear speed is equal to the angular speed when using this equation, and that you can combine those two terms. If it's slipping, then it's not necessarily the case where this v is equal to the linear v, as we said in the kinetic energy stuff. And you usually have to be given additional information. Alright, here it wants to know what is the increase in total mechanical energy of the disk from 0 to 3 seconds. Now, some of you might start thinking that this is looking for only kinetic energy, because it's only mentioning the disk and it doesn't mention Earth. With the C, they don't do that. When they say mechanical energy, they mean kinetic plus potential. That is something new to the AP1, where they're making that difference that kinetic is only for the object and potential is of an object-Earth system. But the C doesn't really worry about it. When they say mechanical energy, they mean mechanical energy. So, we already know the mechanical energy of this. That's easy. It's just going to be the kinetic energy after it reaches that height. However, we do have to figure out this. Alright, so let's get this started. So first, let's find out what the height is. So, that's 0. X equals 1/2 AT squared, where I'll just leave it as AT squared. Alright, so mechanical energy is 1/2 the change in kinetic plus change in potential, change in mechanical, 1/2 mv squared Actually, I should mention that this kinetic is also the linear, translational, plus the rotational. So this is going to be 1/2 mv squared plus 1/2 I omega squared plus mg half at squared. Oh, got a little cut off there. Alright, and this is basically the whole thing. Combine all these things. Remember, it does not slip, so that means that when I use omega equals v over r, that this v is the same as this v. So I'm going to get 1/2 mv squared plus 1/2 of 1/2 mr squared times v over r squared plus mg half at squared.
I can actually pull out a half and an m from each of these terms. So 1/2 of m v squared plus, well, this r cancel out with that r. Half v squared plus, still a half there. G a t squared half m. That's just 3/2 v squared plus g a t squared. Alright, so that means that the change in mechanical energy is 1/2 of m. Now you should substitute the numbers in. I'm not doing that because I'm running low on space. So this is 1 times 3/2 of v squared. Well, we found out before that the velocity was 40. So this is 3/2 of 40 squared plus GA. We said before that A was 1.33. So this is now going to be, so it's going to be 10 times 4/3 times by 3. This is 40. Alright, moving things around, yada yada yada. It's going to be, now ignore this because I'm only doing this because I don't have a calculator. 40 times 1 plus 60. And I get about 101. I think I might have made a mistake somewhere. Okay, I figured out what I did wrong. I made a few mistakes. Oh, can't erase that. Alright. So I made a few mistakes. One, when I was finding out the whole GAT squared, I forgot to square my time. So this shouldn't be 40, it should be 120. And the other mistake that I made was that I did v squared, but I pulled back my old omega. So I have to figure out what the v is. That's going to be 4. My old one, my omega was 40 times by 0.1, so that's 4. So this should be times 4 squared. Alright, so fortunately I can't erase any of this stuff. Oh, yeah. I can't erase any of this stuff. So I should have 3/2 of 4 squared plus 120, which equals to 144 joules. And that's my answer. Alright, this was worth 4 points. 1 point for realizing that the kinetic energy was a combination of translational and rotational. You got 1 point for doing potential energy with this expression for position. You get 1 point for basically combining finding a way to combine the linear kinetic energy with the rotational kinetic energy, whether you rewrote it in terms of the linear speed or you rewrote it in terms of the angular speed, doesn't matter. And then you get 1 point for substituting in all your points, all your values from before to get the correct answer. And that's all you have to do for this one. So I apologize for how messy I was in the few mistakes I made. It's a little bit hard to write on this iPad and know what you're actually doing. Alright, and the last part, it's saying the disc is replaced with a hoop,
same mass, same radius, indicate whether the linear acceleration of the hoop is greater than, less than, or the same as the linear acceleration of the disk. Alright. Well, the way I want to look at this is I want to look at that torque equation again. Tau net equals I alpha. Alright? So let's see. When I replace the disk with a hoop, you should remember that the rotational inertia of a disk is 1/2 mr squared, and the hoop is just mr squared. Now, in this case, tau net stays the same. I'm still dealing with the same force and all that. Everything remains the same. The only difference is the rotational inertia. And in this case, I'm increasing the rotational inertia. By replacing the disk with a hoop, I'm increasing the rotational inertia, which means that my angular acceleration has to go down. And if my angular acceleration goes down, then, if my angular acceleration is down, then my linear acceleration must go down. So, your answer should be less than. And it should be that whole reasoning. Basically saying, you get a point for realizing it's less than, and then 1 point for this type of justification. Now, the way I wrote it probably wouldn't be enough. You'd want to write it in letters, actually in actual words, in English. But I'm just writing this because I don't want to have to write too much on this stylus. So again, the whole idea is that because the forces remain the same, tau net remains the same. You're increasing the rotational inertia by replacing with a hoop, decreasing the angular acceleration, which decreases the linear acceleration. And that's pretty much it. All right. Keep practicing these questions. If you have any questions, feel free to let me know.